Okay, I'm starting now. Okay, we had some technical difficulties, but hello. Welcome back to LispNYC, where we are opening the parentheses to all things Lisp, computer science, math, AI, and in a minute, crypto. I'm your host, Arthur Smiles. If you're new to the channel, don't forget to hit the subscribe and the notify bell so you don't miss any exciting talks in the future. If I were to describe the fundamentals behind the internet, I would say probably the fundamental idea of the internet is about peer-to-peer networking. So I'm very excited to introduce our speakers that are going to take this philosophy to the next level. So our speakers tonight, Richard Kiss, he's a developer who's worked in a variety of startups in Silicon Valley. He's got an MA in mathematics. He's also been a stand-up comedian, and he's the designer of the Chialisp virtual machine and the first compiler for that machine. Bram Cohen is a computer programmer with over 2 decades of experience developing peer-to-peer protocols and software. He's the author of the BitTorrent protocol, as well as the file sharing program BitTorrent. Since 2017, he's been putting his passion and skills in developing Chia, a cryptocurrency backed by a novel proof of space algorithm. Welcome, Bram and Richard. And remember to unmute yourselves.
Is a similar idea to the warning you see.
Thank you. Is this working?
Yep.
Okay, Bram is muted. Looks like he's trying to unmute himself. Bram, you there?
Yeah, I had to click away every single disconnected notification before I could unmute myself because they.
Oh, right.
Yeah. Hey, everybody. Should I give some background? Should I start?
Yep, definitely.
Okay. All right. So Chia, for those of you who don't know, is a cryptocurrency that is based off of proof of space and time instead of proof of work. It is a green cryptocurrency. When you're using proof of work, it involves warehousing for computers, burning electricity, doing not much of anything. And so for proof of space, instead, you can take the over-provisioned storage in the world, of which there is a lot, and without much of any extra electricity on it, sit there farming it and use that to extend the blockchain forward. So we are utilizing this already over-provisioned resource to secure the blockchain. And because that's completely commodity, it winds up being much more, because space is completely commodity, where proof of work is not, but it winds up being much more distributed and secure. And somebody needs to be muted. There's a lot.
Arthur, can you mute everyone but the speaker? This is crazy.
Yeah.
Yeah, there's someone making noise.
Hold on a second. Let me do that again. Okay, Bram, you can unmute yourself.
Okay, there we go. All right. Okay, I think we're set up now.
Yep.
Okay. All right. So there's lots and lots of math and really interesting stuff going on with our consensus algorithm, but that is not the thing we're here to talk about today. So we're here to talk about the on-chain programming environment. You could actually mix and match the Lisp based on chain programming environment we have with a proof of work consensus algorithm. But if you're building a new cryptocurrency from scratch, might as well do everything right. So when we started this, I wasn't sure what I wanted to do for on-chain programming environment. I knew how Bitcoin script works. And some work that people had done on top of that, which has a bunch of insights into how to go about doing things that are helpful. I had some awareness of what Ethereum has done, which has less insights about actually good ways of doing things, but more insights into what things people actually want and are useful. So started working on this, had a bunch of ideas. The history of it is I had some thoughts about what to do that I didn't like. I went over this with Richard and asked him to figure out something, and he suggested, hey, how about we use Lisp, which did in fact fit the bill. So one might wonder, why does Lisp make sense for on-chain programming? There's some background to cover for that. I'm going to try to not get too into the weeds of it. But in Chia, it's in the coin set model, meaning that what it is that's stored on chain, the entire state that full nodes are aware of is these are the coins that are currently outstanding. And a coin has rules about how it can be spent, and it has value. And everything that actually happens involves some coins getting spent and other coins coming into existence. The life cycle of a coin is it doesn't exist, it gets created, and then it gets spent. That's the entire life cycle of every coin.
Interesting.
Yeah. The actual programming of this comes in the puzzles, in the rules about how a coin can be spent, where you have to, which can be specified to be whatever you want. So in Chia, the rules for spending a coin are that there is a Chialisp program, which the coin is going to run. And in order to spend the coin, you have to create a solution to the puzzle. The solution will be passed to the puzzle, and the puzzle will then return a list of conditions, which either are or are not met. And if they're not met, the spend doesn't happen. And if they are met, the spend can happen. It is valid. That's the high level view of the thing. On its face, this sounds insufficient to actually do reasonable programming. Particular the sorts of things like supporting asset tokens that we want to do. There are some clever tricks that actually make it possible to do something with this, that are supported by a number of features that Lisp actually has very well. So the two big things that come to mind here are, number one, no side effects. Actually, it all centers around one thing. The main thing is you need to have eval.
Yeah.
Eval is no bueno, like no good, don't do it ever. In Lisp, eval is okay because the data structures that it uses in the language itself are the same as the data structures that it uses for data, and because there are no side effects at all. Those make it possible to have this kind of very self-referential style of programming for that to work. And that was very, very important because basically everything that enables you to actually get anything done in programming involve kind of two tricks. One of them is you can kind of implicitly remember stuff without having it sitting around on chain by saying, well, there's something that might be done here, but I don't remember what it is. I remember the hash of the program involved in it. And I need to be given that program, and then I'm going to check that it has the hash that it's supposed to, and then I'm going to run it. Essentially creating a Merkle tree if you do this many layers deep. So that is one of the essential tricks that needs to be enabled. That could be done in, well, all this could be done in non-LISP-like things, but it gets much unclear. And the other one is that you need capabilities of some kind. You often want something where there's a coin that has identity or value or something that you want to not be counterfeitable. So this is, it needs to be able to prove that it is what it claims. This is an NFT, or this is an asset token. This has some kind of capability, and it's important that this thing be able to prove to other things on chain that it is what it claims to be. So this is enabled by the other trick, which is the only really original idea of mine in the whole thing. But the other trick is the jargon that I like using for it, which apparently is opaque to most people because this is Bitcoin jargon. You can implement capabilities using covenants that point back in time. So the idea is you're going to have something that says you're going to have a shell around your puzzle. And it's going to say, well, I'm going to only make, say in the case of an NFT, I'm only going to make one output that's going to be the new instantiation of the NFT that I represent. It's like the reincarnations of the Dalai Lama. There's just a new one to replace the old one each time. And I'm going to make sure that I am the real one. So in order to make sure that I'm the real one, I need to be given information about who I am, and I'm going to check that my parent is either the originator of this NFT or also follows this same format where there's this wrapper around its puzzle. And so the puzzle wrapper is enforcing that. So you can deduce recursively that you are the real one. Your parent followed the rules, so their parent must have followed the rules, so and so forth and so on. So at some point, you hit the origin of the whole thing. Ergo, you are. This is done using secure hashes and the format of how coin IDs are generated. They include their parent's ID and their puzzle ID hash and their amount. That's
Now I do have a question. Like in just to understand this coin concept better. So like in Bitcoin, right? Essentially, it's a ledger-based system in the sense that you basically have wallets and you have amounts, and then the numbers move around. In this case,
no. The wallet concept is a UX thing in Bitcoin. In Ethereum, it's not, sort of. But in Bitcoin, there are also they call them UTXOs. And there's some really implementation ugliness going on. There's a lot of cleanup of all this that happens in the Chia programming model. So in Bitcoin, the first class objects are the transactions and the actual things that sit on chain, the things that we call coins. Those are identified by the ID of the transaction that created them and the index of which of the coins that thing created they are.
Okay. Yeah, that makes sense.
Yeah, that's kind of ugly. That's problematic in a number of ways. It's much, much cleaner and prettier to do it the way it's done in Chia. There's a number of other cleanups that are done. Like in Bitcoin, there's an order of all the transactions that happen in a block, and that's not true in Chia. In Chia, they all happen simultaneously, which is very important for a lot of functionality that happens, actually. It would not be possible to have proper asset tokens without that.
Anyone now can buy oil for free, and the contract will just
somebody again.
Just because the contract believes that the price of Ethereum is zero. And not only that,
can we mute?
the thing that will happen is that all of the projects on the same manipulated oracle or compromised oracle will get hacked.
Okay, we're back.
Okay, good.
Yeah.
Yeah, I have a feeling people might have a lot of questions about this. I'm perfectly happy just answering questions as people get questions.
Mm-hmm. Yeah, the floor is open to people.
People are sort of asking questions in chat. I can answer those.
Yeah, let's do that.
Okay. Someone asks, why not use an account model? Well, that's the question that's been asked so far. So the account model is complicated, and it doesn't really help you all that much. What you really want for anything that's consensus critical is for it to be as simple as it possibly can be and as well defined as it possibly can be. And the account model in Ethereum is really based off of just kind of throwing a bunch of mud at a wall and hoping that something sticks, right? It's, well, we don't know what would actually be useful, so we'll make something that can do anything. So they made this thing that looks like web development. So in Ethereum, in the EVM, you have a contract, and the contract has a program that's written in bad JavaScript, which it's running. And it has a lot of very, very rich state. And it turns out being able to reason about that is really, really hard.
I totally agree with that.
Being able to figure out what could happen to that program and proving that there's not some security problem is extremely difficult. That's very different from the coin set model, where, I mean, it's still not completely trivial to prove how things work, but you have this huge leg up in terms of reasoning about everything. It's really designed with like auditability and security first in terms of how it works. And it turns out also, it's in many ways much more powerful. Like in Ethereum, there are ERC20 tokens, which are very hobbled in terms of their functionality. An ERC20 token just means there's this program that's running on chain that's remembering what everyone has. And in Chia, when you have an asset token, and we're in the process of finalizing our standard for doing this, when you have an asset token, people control their own coins. Their coins are real coins that can be interacted by other smart coins that their wallets can hold themselves, and have all the type of functionality of vanilla Chia, which includes actually one really amazing bit of functionality, which I'm very proud of and excited about, which is you can make offers. So if I have this idea that I want to trade a certain amount of Chia for a certain amount of some asset token, I can make an offer file. I can make a partial transaction, something which is not itself a valid transaction, but is partway there. So I can make this thing, burn a bunch of Chia and print a bunch of this asset token. So this is not valid. You can't print asset tokens out of nothing. But I can then take this and just mail this to my friend, post it on Reddit, do whatever. And if somebody decides they want to take the other side of this, they make a balancing offer. They make something that prints the amount of Chia that I burned and burns the amount of the asset token that I printed. And they smush these together. And because everything nets out to zero, this is now a valid transaction and will actually go through if they post it to the blockchain. That's also part of why it's so important that all transaction, everything that happens in a block happens simultaneously.
And I actually, just to follow up on my earlier question too, like you mentioned how a coin, coins get created and there's a value on them, and then they get spent and the coin's destroyed. Now, when you spend that value, that number, the way you spend it, does that number transfer to someone else's coin?
Well,
Or how would I transfer that value when you say it's spent, right?
Yeah.
Um,
So the
how does
coin
it get transferred?
Right. So a bunch of coins are spent together as part of the same transaction or in the same block. In Chia, a transaction is a really mushy concept. In Bitcoin, a transaction is one big thing, and every UTXO involved signs the same transaction. In Chia, it's a much mushier thing where each coin is individually spent, and they may have interdependencies on each other.
Okay.
One of the ways they can have an implicit interdependence on each other is there might be a coin that's spent that creates children whose value is greater than its own value.
Mm-hmm.
And this is not allowed. But what can be done, what Chia allows, is for everything to just kind of net out. If there's another coin that makes children whose sum total is less than the parent's size, and that balances out with the amount of excess creation that some other coin does, this together now makes a valid transaction.
Mm-hmm. Okay. I think I understand it better now.
It kind of sounds like garbage collection is involved here. If there's no reference to a coin, if it has no value, then it's collected. Is that how?
Coins are, every time, a coin is not a persistent thing. A coin only gets spent once. As soon as it's spent, it's toast, it's gone. One of the fundamental building blocks of smart coins is singletons. That is a chain of coins, all of which inherit the same soul, the same capability. So if you want to have an NFT or a DID or a rate limited wallet, all of those immediately start at their very beginning with having a singleton, because that is not something that is supported by the underlying CLVM in an obvious form. It's something you have to implement yourself.
Okay, we have some other questions. The questions are streaming through. Okay, Scotty DFI asks, I thought I had read about asset tokens being able to incur debt. Does that mean you do not need to burn Chia at a 1-1 when creating the tokens?
I'm not sure what that means. Sorry.
Okay, while that's going on, okay. In the meantime, Richard, do you want to talk a little bit about? Oh, let's see if it's fixed or. While he's going on, figuring out what's going on with the alarm system, Richard, do you want to talk about a little bit about Chialisp?
Well, I'm not sure what the level of knowledge of our viewership is. I don't want to start too simply, but I don't want to. Are there any, maybe I could handle specific questions? What's happening with Bram?
I think an alarm went off in his house, so we need to switch speakers. So, anyways.
Sorry, the smoke alarm went off.
Yeah. It's like, well, anyways, we've been having a lot of gremlins in this particular stream, anyway, since the beginning. So I'm not surprised.
Whatever it was that caused that was something which I had no control over whatsoever. It looked like it wasn't even my alarm that was doing it. So hopefully that doesn't happen again. Sorry. Okay. Someone have a question?
Go ahead, Arthur.
Yeah, let me go back to the question. So I think you were in the middle of answering about that. I thought asset tokens incur debt. Does that mean you don't need to burn into one?
No. Asset tokens are very cash and carry, right? Like asset tokens are hard money. You have it or you don't. you can loan someone tokens and they can owe it to you, but that's a loan. That's a normal loan. When you have lending, you have creditworthiness. That's that is unchanged by cryptocurrencies. There are things that cryptocurrencies do and things that cryptocurrencies don't do. One thing cryptocurrencies do is allow like very fast transfers of money between peers who don't trust each other without having a trusted intermediary in the middle, and all kinds of programmatic constraints can be put on this. What you can't do is have lending without creditworthiness. That's not a thing.
By the way, you guys, you can also, if you want to ask the questions directly, by all means, you can interrupt. But Bidey Crypto Tour asks for you to elaborate how, well, we can maybe do this later, but how Chialisp handles concurrency.
So the way cryptocurrencies work is real cryptocurrencies, not these things that people are playing with. The way real cryptocurrencies work is you have a blockchain. You have the history of the database, which a certain amount of work went into creating, some difficult thing to do, either proof of work or proof of space and time. That's basically your options. If you and I get into a discussion of what is the current state of the database, we and whichever one has greater weight, whichever one had more stuff go into making it win. The vast, vast majority of the time when there's a discrepancy, it's because one of us has a subset of what the other person does. There's more stuff added as the blockchain has moved forward in time. So you have this secure hash-based series of blocks. Everything that happens inside of a single block in Chia happens concurrently, but it happens after everything that happened in the previous blocks. So at the time of a block, the time of a transaction block, in Chia there are blocks that don't make transactions, but within a transaction block, there's some state of the coin set, which is technically speaking a map, because each coin has a birth date. There can be requirements that coins be a certain age in order for certain transactions to go through. But at the beginning of it, you have a bunch of coins that are currently outstanding. And then all of those, some number of those coins get spent. All of those coins that get spent in that block get spent simultaneously. And then all the coins that are created in that block are also created simultaneously from the point of view of Chia. So that's, I hope that answers the question. It's important for communication between things. Like if a coin wants to has the permission to create an output, but then wants to make sure that that output gets spent in a certain way, it can require that it get a message from its grandparent that it was, from its grandchild that it was spent properly. And that way the grandfather, the father and the child all must be spent simultaneously in the same block. That's a totally normal thing to have happen.
So basically, I mean, concurrency is different than the way we would think about it in regular programming, because usually when people talk about concurrency, they're talking about, oh, I want to do multiple processes at the same time. Where when you're programming coins, you're really focused on your own coin, and the important thing of the timing is the time dependency of when these blocks are written. Is that correct?
Yeah. You don't. I hear a fire engine now, so I hope I didn't turn off a legitimate alarm. That would be annoying. When you have things that are consensus critical, it's very important that the way that they get executed be the exact same way on everybody's machine. It needs to be completely well-defined what they do. Otherwise, when different peers try and validate the same block, they might get different answers, and now we have different versions of the blockchain, and that's no good. That's very, very bad. yeah, so it's very important that there be really no timing involved in how the concurrency goes. Now, because all the transactions in a block are simultaneous in Chia, you can have quite a bit of multi-threading going on in validating a single block, although also more importantly, the way it's architected, each block can be validated in a separate thread. So when you validate a block, it boils down to, yes, this validated, and here are the coins that were spent, and here are the coins that were created. And the thread that's doing the validation just boils it down, everything about validating the block just down to that. And that's a very small amount of information. So then the serialized portion of the whole thing can be run very quickly once all of that is done.
Cool. And here's a question from YouTube. Gerald Neal asks, for Bram, the first block you put a comment crediting those who came before us. We stand on the shoulder of giants. Other than the obvious one, who might that be? Any Lisp folks?
Yeah. So Chia is very directly based off of Bitcoin. So it has the UTXO model that Bitcoin does. So that obviously came from Satoshi. The other people I spoke to in understanding what was going on and figuring out what's happening, there's Russell O'Connor, who made Simplicity, which is one of the ancestors of Chialisp. There's Andrew Miller, who did a bunch of analysis of how things can be done in the UTXO model. There's Greg Maxwell, who came up with Taproot and Graftroot, which we most definitely support. There's Peter Willey, who's also done work on the core of Bitcoin and that kind of stuff. So those are the immediate people who come to mind.
And one more from YouTube. Okay, so this was a question about if I have £1 equals one exchange, the color coin allows you to split this into 50 pence, 20 pence. I mean, can you basically subdivide the value?
Yeah. You can subdivide Chia. The minimum subdividable portion of a Chia is a mojo, and there are 1 trillion mojo in one Chia.
Okay. So yeah, you basically can go all the way down. Got it.
Yeah, but you can't subdivide any further than that.
Yeah. It's basically a Chia is just so you don't have to count in the trillions.
Yes.
Future. Okay. That makes perfect sense. And I think and Sophia asks, so is there no possibility for reentrancy in Chia scripts?
There is a lot of reentrancy in CLVM programs. And there's 2 levels here. There's what do you do in Chialisp, which is a higher level language, and there's what do you do in CLVM, which is what it compiles down into. Actually, maybe Richard can better talk about exactly how reentrancy works.
Well, when I think of reentrancy, I think of a program running, calling a function and having that function call itself later in the stack, which I guess you can do.
Like one of the first things I did in CLVM is write a factorial function as a good example of how you do this. So if you want to write a factorial, what you do is you have sort of the outer factorial and the inner factorial. And what the outer factorial does is it passes the inner factorial function to itself along with the number of iterations that need to be done still and what the value is up to so far. And the inner one multiplies the value it was passed by the number of iterations remaining. And if the number of iterations remaining is 0, it just returns the value it has. And if the number of iterations remaining is more than 0, it calls itself, which it has because that was passed in, and passes it 1 less the number that got passed to itself. That's how you do reentrancy.
Yeah, you have to do a Y Combinator style trick, passing the function to itself so that it can call itself recursively.
Yeah, the CLVM is extremely minimalist. Whether Lisp, people who actually program in Lisp view Chialisp, or well, CLVM, not Chialisp, but view CLVM as the essence of Lisp or a horrible brainfuck style parody of it. I'm not really sure.
Yeah, I like to say CLVM is if Lisp, an assembly language, had a baby.
Yeah.
And then you put compilers on top of that to compile to CLVM.
Mhm.
But the idea is CLVM is simple to implement and eyeball, make sure that it's regular and bug-free as possible. And you put all the fancy stuff in the compiler.
Yeah, at one point, actually, Richard had a prototype, and then we discussed it, and then I kind of rewrote it based on my understanding of our discussions, and I did that like in one evening. And what we have now is mostly Richard's Chialisp with my conditions language. It was I mostly re-implemented just so I would have a convenient way of expressing my ideas for how the conditions language should work. We don't have a name for the Chia conditions language. We just call it the conditions language. You can't really do anything with it. There's like this very short list.
Right. Well, I mean, it's a language like how HTML is a language. It's really just a data structure.
Oh, it's dumber than
you
it
doesn't really compute anything.
Well, maybe you can just go briefly in what that condition language is. Like, what's its primary function? Is it just to figure out?
Yeah, it's the output of a. So a coin has a puzzle associated with it, which is my silly name for what locks the coin. And when you try and spend a coin, it runs the puzzle program, and the input is the solution, which is just another CLVM data structure. So a cons box or an atom, and the cons box can have more cons boxes and so on in it. So it uses that as the input, and it's expected to produce an output, which is in this conditions language. So it's a list of it's a Lisp list of conditions, where conditions are things like assert my age is at least this many seconds, and also there are a few commands in there too, like create a coin or create an announcement. An announcement is how one coin spend communicates with other coins spent in the same block to say I've been spent and I fully support this operation, where the operation is encoded in the announcement. But when you spend a coin, one of the condition outputs can be create coin, which is what creates a child coin of that coin. And that's the only way to create a new coin, is by creating an output condition create coin.
Okay, and I guess that's also essentially how the Chia thing started. There was one big coin, right? That then you created other coins from. Was there like
no? Every
are they created?
Yeah, every block there are farming rewards for creating that block, and so those have like a special parent that's just an encoding of the height that they started at, and that's the original thing that has no parent.
Cool. So if there's no more questions, if you want to continue.
Well, I'm seeing a bunch of questions.
Oh, okay. If you see a question, you go ahead and answer it.
By the way, in Bitcoin parlance, if people know that, what we call a coin, Bitcoin calls a UTXO, sort of. These are reasonably analogous. What we call a puzzle, Bitcoin calls a script key, and what we call a solution, Bitcoin calls script sig, which are names the Bitcoin names only make sense if you're a cryptographer. and Richard got very confused by them, so he started calling them puzzles and solutions, and that's what we've been using since. Someone asks, Solana stopped producing blocks. How do we keep that from happening? I can't speak to what Solana's problem is, and I don't really want to speculate about exactly what their issue is. Crypto, like real cryptocurrencies, and Solana's consensus algorithm is not like this, unfortunately. But blockchains that actually use Nakamoto consensus are by nature very, very robust, because you can always make your way out of a hole, basically. No matter what's going on in the network, no matter what's happening, if you and I get into a discussion about what is the current state of this database, and we can, with no input from anyone else, decide which of us is right, because we can look at the blockchain histories that we have locally and compare their weights, and whichever one has a greater weight wins. This will always give you an answer, and it will always achieve consensus after some amount of time, even if there are horrible splits going on. And one hopes that you don't normally have constant horrible reorgs, because that would be very, very bad. One hopes that you don't wind up in a situation where there's only one entity who's making all the blocks, because that also would be bad. But it is a very fundamentally robust approach to having consensus. And we are following Nakamoto consensus in Chia. That doesn't mean that you can't have issues. We did one time have a slowdown. It wasn't actually, the chain didn't actually stop, and it only slowed down for half an hour. That was caused by, we had a bug, which just caused some issues. And because everyone was running the exact same piece of software, the bug hit everybody. So we were able to fix it pretty quickly. In the future, we're going to have more auditing of our code base, and we'll hopefully have more implementations, and that will be less likely to happen in the future. But Chia, as a Nakamoto consensus-based cryptocurrency, is designed to have the property that we could go away. Like everyone at Chia, the company, could just blip off the face of the earth, and Chia, the blockchain, would just chug along. It would continue to work, no problem. Like everyone who's currently farming could just disappear. Whole new set of people could join, continue, no problem.
Yeah, I actually got another question. Oliver Mesh from Keybase asks, well, I'll read the statement. Thanks to your suggestion a while back, I've been working on my way through transaction processing and the universal computer. Are there any other books or other media you recommend?
Oh, well, right now you can go to Chialisp.com.
There you go.
Let's start
Chialisp.com. Check it out. It's in the description too.
Yeah.
Cool. And I think we got everyone's questions here. Oh.
Yeah, there are some unanswered questions here. Let me pick out.
Oh, okay. I do have another question from Gerald Neal on YouTube. He asks, seems to me that the unique aspect of Chia lists compared to other lists is heavily focused on SHA-256. I'd like you to elaborate on what is there a heavy focus on it, or is that important about the? Yeah, go ahead.
Sort of. So if you look at CLVM, and compare that, I'm being a little bit speculative here because I have never really written very much of any Lisp. So CLVM is my own, me and Richard's sort of vague reconstruction of Lisp based on certain criteria that we have that it meets. So it's a little quirky, but one of the things is we only have one type of atom, right? So like there's no, so nil, quote, 0, and empty string are all the exact same thing. The data in those is non-differentiable from each other because atoms don't have type. And the type is inferred by the operator that you apply to them.
Okay.
And so to the extent that SHA-256 has extra weight in the language, it's because we have very, very few operators. It's like plus, minus, concatenate. Really not very much that can be done. But one of those things is SHA-256, which is unusual to have as one of your 10 primitives or whatever the number is. But we have it because it's so important for on-chain programming.
But so just to follow up on the question for myself, the purpose of SHA-256 is primarily for creating the puzzle, right? So you can use any, you can probably, if SHA-256 were to be attacked as a crypto, let's say there was a discovery of a weakness of that crypto.
Oh man, the
whole hash.
SHA-256 fell apart.
What?
Everything is based off of SHA-256.
Oh yeah, I know that. I'm just saying, or would you have to just change the software fundamentally? Is it part of the protocol itself, or is it something that's built on top of the?
Oh man, if SHA-256 were broken, that would be bad. The primitives that Chia uses there's SHA-256 just everywhere. There's BLS signatures as the digital signatures that's used. And there's repeated exponentiation in a class group. So for our verifiable delay functions in the proofs of time. That's some interesting math right there. But
I actually tried to go through the white paper, but it kind of felt like my brain splattered. So out of a giant building in Jupiter, basically.
So our green paper is not late reading. And actually, the primitive that we're using is now the second generation of that. I iterated on it and came up with a more complicated thing that's much better, which is what we're actually using. And we're working on a hopefully much more readable, although much more expanded paper. That's the green paper too. But yeah, the green paper is not a white paper per se. It's a piece of technical information. But of those things that I just rattled off, BLS signatures and the class group operations are not terribly quantum resistant. So there's questions of what you would do if you have a quantum attack on those things, which I don't think is happening for decades, if ever. That would be a big, massive, huge quantum attack. There are contingency plans that are really technical and involved, actually, about how you would go about doing these things. That a bit involved to explain that stuff. But SHA-256 is not is quite quantum resistant by its nature. It's a symmetric cipher primitive, and symmetric cipher primitives quantum is not scary at all. It's only public key things where you get into those issues.
Okay. Let's see. And by the way, the people on the chat here, if you'd like to ask directly, you can also just raise your hand, and then you can unmute yourself, and then you can ask these questions directly. So we can hear other people besides me. Let's see. One of the interesting things is as soon as I said green paper, I got a whole bunch of comments saying white paper. It's green paper, not a white paper. Yeah. So I don't actually know what the difference between a white paper.
So white paper, as people use it. So our green paper actually is a lot more like the original Bitcoin white paper. White papers these days, what people use for white paper are mostly marketing materials for ICOs. Since we did not do an ICO and have no marketing materials for our non-existent ICO. We don't have
Mhm.
we do have something we're calling our business white paper. We do have something that explains what our emission schedule is and how we're structured as a company and things like that. And it's all really normal and boring. And our green paper really explains the fundamental insights of what we're doing. That when the whole thing started, I had this idea of like, hey, I know what we can do to get away from proof of work. What we need is proofs of space and proofs of time, and then we can stitch them together. And that was my idea. And it was pretty hand wavy. A bit of advice I always give to people is when you're doing a new startup, don't have invent new math here anywhere on your product roadmap. And I'm a total hypocrite. We had 3 of those, actually 4, because we didn't know how our Unchained programming environment was going to work either. But got away with it. Our advisors invented proofs of time. I personally invented the proofs of space primitive that we're using. And then I figured out how to stitch them all together. Both of those last 2 were in collaboration with one of our advisors. So yeah, that was a bit of a shenanigan, but we made it.
It's awesome. Okay, and we have another one. Nope, I think that's it on the YouTube. So anyways,
so someone asks, is there any message passing in Chialisp?
Yeah, I missed that one.
Yeah. Yes. When coins are spent, they can make announcements. It's called announcement because technically speaking, any other coin can read it. But when a coin is spent, it says, here is this announcement that I am making. And that the announcement is just a string. And other coins can say, I require an announcement from this coin ID, and it must say this. And that's how coins can communicate. It's kind of like both ends are told what the communication is, and they're just verifying that it's happening with their communication with the chain. These are more powerful than it sounds like, because you can do things like be given a reveal of the puzzle of the coin that's making the announcement, and then verify from its structure that actually is an asset, a proper non-forged asset token. And there's a lot of that kind of logic that comes up. That's all this like recursive stuff that's happening. We also have another quirk I'd like to mention. I don't know if anyone cares, but the way our quote works is it doesn't eval the thing on the right. So you don't have all these lists of length 1 to parse out. It just takes the thing on the right verbatim because quote is already special for the interpreter. Mm-hmm. So that was just us being parsimonious of the size of our programs.
Well, I did find it interesting the way so like in most lists, quote is so kind of fundamental that they just end up using a symbol, the single I guess the apostrophe symbol.
Yeah, we use
that's like basically it says whatever comes after this is quoted. So if you want to quote a whole list, you just say like apostrophe and then open list, and you just write it in there, and then that's the list verbatim. But and I noticed in Chialisp that you have like an operator. So it's you have a list. Basically, it looks like any other operation where you have, and you can do that also in like Common Lisp, where you can say like quote and then something.
The thing that people say is quote often in Lisp is actually a higher level thing. It's like what we call a quote, and I am very against using it in Chialisp programs in general because it has potential security problems if jokers throw in the escaped strings in their own programs.
I see.
So it's a really, really low level primitive thing. But our interpreter, its control flow is like really super, super specific. It just evals everything with the exception of quote and
apply.
And apply, and if it encounters a number, that counts as a parameter lookup. But those are the only special things it does. Yeah. Quote, apply, and look up a parameter are the three ways in which the interpreter can get derailed from its interpreting. But that's the only way. That's all it knows.
Cool. Let's see. Do we have any other questions? I don't see any specific.
I'm seeing.
Oh, I do. I found one on YouTube. Gerald Neal asks, do you guys advise a young programmer to learn Lisp early on before other languages? For example, Scheme and online MIT courseware versus Python, etc.
So Chialisp programming is a super special thing. It's like, it's like PHP. It's a special purpose language that only makes sense in this one particular context. Lisp is a really good fit, I believe, for that particular thing because it is eval-based programming. It's like it's a form of programming where saying, okay, I'm going to be given a snippet of code and I'm going to check its hash and then I'm going to call it is like just a totally normal thing to do. And you just can't do that in normal imperative programming languages in the slightest. But if your goal is to do on-chain Chia programming, Chialisp is a great starting language. And the Chialisp tooling is not super mature right now, although we have done some stuff in it. And it is in some ways a whole lot nicer than Ethereum programming. It's slower to get a first crack of something out, but in terms of like writing real robust projects that are full featured and reliable, it's much better for that. For some people, it may be a good first language for that reason. And it is very anomalous in many ways as far as being a programming language. But for many other tasks, people don't usually do those in Lisp. And you certainly wouldn't do them in Chialisp. That would be insane.
Learn Lisp early, late, or never. I mean, learn Lisp early or late, but not never. And Scheme, of course, is a Lisp, so you can certainly learn that first.
There's definitely an argument to be made that learning Lisp gives you certain insights into programming generally. It definitely does that. Although it's, if you're a beginning programmer and your immediate concern is getting a job, actually, I don't really know what people hire, how many people there are hiring for Lisp. It's a niche.
Mm-hmm. Well, there's Clojure. There's a lot. There's surprisingly a lot of stuff that's done in Common Lisp behind the scenes.
Oh, okay.
But yeah, so there is stuff. Okay, Ram asks, what sorts of tooling is available to do Chialisp programming?
Yeah, so technically speaking, Chialisp itself is tooling because Chialisp compiles into CLVM code. And you really don't want to try and write CLVM code directly, although we've done so in places. If you go to chialisp.com, there's stuff. We're improving our tooling in general. We're dogfooding the whole thing as we do it. We made our pooling protocol. We're making a bunch of things. We're making standard libraries. So we're making standard singletons and an asset token standard. Those aren't fully baked yet, but we're in a few weeks, we'll be there with those. So that's a good starting point. Just the general way you go about doing things. We're improving how those tools work. And they're getting quite a bit better very rapidly.
Cool. Let's see. Dennis from YouTube asks, are Chia coins like an Excel formula but cryptified, i.e. you can tell the coin to do whatever you like within the system parameters and the script is called a puzzle?
Yeah, well, a puzzle is an arbitrary program. You can have any CLVM program be your puzzle. And the puzzle gets past the solution. When someone wants to spend it, they make CLVM data structure that is the solution, and that gets passed into the puzzle. But you get this like craziness where it's really normal for part of the solution to be another Chialisp program, which the puzzle then calls. It happens all the time.
Cool. Let's see.
I think someone did write a Chialisp atom mode. Someone's asking about that. we actually have two things. There's
What's a Chialisp atom exactly? What is?
Oh, Atom, the text editor.
Oh, okay.
Yeah.
Oh.
Well, it's so the atoms. There is the term atom in Chialisp, which is just a primitive. So everything in CLVM is either a cons cell, which is the same as a cons cell in any Lisp, or it's an atom, and an atom is a array of bytes. Where if there is an operator working on it that treats it as a number, there are rules about how it's parsed for that. And if it's being parsed as an array of bytes, there's rules around that. And if it's being parsed as an operator, there's a lookup table of what all those means. But like I said before, quote, empty string, nil, and 0 are all the exact same thing.
I think you might have invented a new, the LispNYC's Facebook group. You can check that out. Look it up on Facebook. But there was a discussion about static typing versus dynamic typing. And I think you came up with a third idea, which is typing based on operator.
Yeah. I mean, it's not very safe. It's not, like the type information is not there. Like it's very almost C style in that sense.
Yeah, well, that's how it's like assembly language, really.
Yeah, it's weak typing, so I mean, it's what C has.
Yeah. Do we support what's the term in C where you say, I'm going to pretend that this is this other type. Just trust me, it works.
Type cutting?
C's equivalent of casting.
Yeah, casting. Yeah, there's.
I mean, like in other languages, casting means different things, which is all kinds of fun.
Yeah. I don't know Chialisp's status of casting. Chialisp is not. So CLVM is baked in time forever. That's never going to change. But Chialisp is potentially a little bit of a moving target that it's going to be likely extended in the future.
It doesn't have any typing right now, but that's something that we definitely add.
If the type is determined by the operator, then it's possibly a bit more like JavaScript in that it coerces maybe the object to that type when it sees it, as opposed to like it's basically weakly and dynamically typed, you could say.
Yeah.
Or like Forth, right? Forth is a lot like that.
Well, I mean, you can either expect a cons or an atom. And so if you have an atom, it doesn't matter if the atom was originally encoded as an int or as a string or just as a blob. You can just interpret it as the wrong thing, even.
Which is a lot like what happens in Forth. Yeah. It's the operator that decides the type that the operand gets interpreted as.
Yeah, and apply like just takes a cons box. Like you can just take any old data structure and say, here, run this. Call it.
We could teach the compiler about the expectations for each of these operators, and then it could do some type checking. Plus is going to return something that you expect it to be an int, and if then you pass that to substir, it might say you're trying to take the substir of an int, which will give you something, but maybe not the thing you want.
Yeah, our compiler is currently in the process of being rewritten by someone who sort of knows compilers, as opposed to us people who wrote it originally who don't know compilers at all. So it's maybe quite a bit more featureful in the future in terms of what it's willing to check for you and such.
Compilers are easy. That's one of the morals of the Lisp community.
Definitely. Well, certainly writing a Lisp interpreter.
But compilers too. They're not hard.
Yeah. I mean, but writing a good compiler is difficult, but writing a compiler that works is easy.
Yes, hence our ability to actually have gotten a compiler working okay. Without
Well, I found that as soon as you get one that works, then you see, oh, I can add this thing, and then you add that thing, and that now leads to 2 more things that you see you can add, and it just sort of grows exponentially.
Yeah. Well, that's the pathway between working and good. And if you take that path wrongly, then you end up going from working to worse.
Yeah.
Excellent.
Yeah. So we're in the process of I guess a complete refactor of a just total rewrite of the Chialisp compiler that we're using standard, because it's being done by someone who knows what they're doing. But it's not changing the syntax of Chialisp per se, which I don't think anyone's really complained about. So people seem happy with it.
Just to follow up on, someone on YouTube wants to follow up on before you were talking about the insights that Lisp offers. So he says, sorry, Bram said there's an argument that Lisp offers certain insights to the computing. What does he think they are? So what insights do you feel that you got maybe from Lisp?
So there's kind of 2 ways of thinking about things, about the world. You can, and at the extremes of ways of thinking about things, you have the all imperative way, and then you have the all recursive way. Mm-hmm. So, and people, like, practical programming is often very, very steered towards imperative in terms of how it goes about doing things. Little story from when I was a kid. I didn't really know how to program. I was like 12 years old, and I was writing a program to play Connect 4. And so I read in a book how to do alpha beta printing. And so I implemented alpha beta printing, but I didn't know recursion. So I wrote some code to do a 1-ply look ahead, and then I wrote another function to do 2-ply look ahead, and another function to do 3-ply look ahead, and so on. And I was like nesting these in each other. Actually, they were inlined. It was deeply nested. Yeah. And which is, it's funny because this is actually a very and also I didn't understand local variables. So I just had, I created my global data structures at the beginning of the program, and just made an array of the data structures I would need at every level, and just passed in the index that it was in as it's going down. This is actually a very performant way of writing code, and very, very difficult to do. I was doing it because I didn't know a way of making nicer code, and I was sufficiently naturally talented that I could get away with this ugly stuff.
I mean, it's what a compiler would do if you told it to inline.
Yeah, exactly. So I eventually got like 8 levels deep, and I figured out the pattern, and I just wrote 2 functions for the first and second player that called each other, and wowie kazowie, much nicer code base. So it really helps to be able to think, if you were to do something in an extrema of recursive programming versus an extrema of iterative programming, how would you go about doing it? There's some amount of mixing and matching that I believe could be done in terms of the way data structures work, because like Lisp bundles together everything is recursive with everything as a cons box. You don't have to bundle those together. You could mix and match if you wanted to be goofy, make theoretical languages which are like all recursive and have imperative style data structures, or are all imperative but have all like cons style data structures. Those are completely doable things, but there is that you could do. It might look a little demented when you were done, but that could be done. And making those languages and programming in them for fun might also give you further insights into the nature of software and programming. But there definitely is a logic to putting together bundling together everything's a cons box and everything is recursive. And it has its place. It's definitely great for on-chain programming, like we were just talking about. Makes your tooling really simple to build, at least relatively speaking. It's not the dominant paradigm in programming. So for most things, people are finding it more convenient to do things other ways. It certainly is, outright bad for like true performance, right? Like if you really, really want the most performance you can get out of a practical computer. You're not going to be writing low-level things in Lisp. But
I just want to gently disagree with you. SBC,
Okay.
I would like to disagree with you because
okay, that may be a controversial statement in these circles.
there are people have solved that problem. But,
Okay, well, well, we actually have a lot of very mathy stuff, which is actually big chunks of it are either written in assembly or are written in C that's very aware of how it's going to get compiled. And there are certain types of things where you just really need to write them for the quirks of the architecture that you're on. And particularly, you get into things like verifiable delay functions that are very critically dependent on IFMA to work well. And you're getting there's really, really scary assembly that we have that does that stuff. So there are places where you just are going to really need to know, I think, about the hardware. There's controversies about how good could compilers get really. And there's definitely been huge improvements made there, even for things that are bad for it, like PyPy was just this crazy pipe dream in the past. No, it kind of works very well on certain things.
yeah.
Well, you know, the assembly language of the computer you're using, not so much. That's being compiled at runtime into something much lower level that's closer to immutable. Down in the weeds.
Yeah, you can get, depending on exactly what you're doing, you can get much closer to that thing if you're really getting into performance crazy stuff, which we did in a few places in the Chia code base, specifically for verifiable delay functions. There's a lot of that going on. Also, the BLS signature checking stuff. We didn't write that, but that does involve some super crazy things that are really, really particular. Not quite as much as the BDFs. Hey, I have a stop now. Have to get going.
Okay.
So
Great. I think Richard, you're going to continue, right? With the presentation.
Yeah, I can answer some questions or.
Okay. Well, before you go, there's actually one more comment I'd like you to hear because I think you might like it. I think that Chia deserves a neat. This is from Nicholas Zagorak on YouTube. I think that Chia deserves and needs a good social network, like a community website for farmers. Is that farmers?
Yeah, farmers.
Farmers, developers, and anybody anybody interested. So I'm going to make a social network for all of us. So we might have.
Yeah, just make sure to call it unofficial.
There you go. You want to make your own thing about? I know that there's a thriving community on Keybase, which is how I was able to get in contact, and I see a lot of stuff going on there. And their website, Chialisp.com, you guys can check out. But yeah, I think everyone wants, the bigger the community, the better. And of course, you have LispNYC as the place if you'd like to show your project to the rest of the world.
Yeah, no, we want there to be a much bigger ecosystem than there is right now. We foresee in the future the vast bulk of development is done outside of my company, right? That we have this big ecosystem of people working on all kinds of stuff. And what we're trying to do right now is enable that. We're trying to lay the foundation to make it possible for other people to do that stuff.
Awesome. So I think with that, since you have to go now, first of all, thank you for answering all these questions. We had a lot of great questions from the audience here. We're going to continue the discussion. Richard's going to do some demos for us. But yeah, I just wanted to personally, before you leave, just thank you for sharing your insights on this stuff. And I'm looking forward to see more things going on with Chialisp.
Great. Yeah. No. If anyone wants to pick up Chialisp and start building stuff on it, great. Please, come in our Keybase channels, look up our stuff, give us feedback. Have at. All right.
Yep.
Bye, everybody.
See you later.
Bye.
So, okay. You've been quiet long enough, Richard. So, yeah,
well,
discussion continues.
got some big shoes to fill. So I can take some, do some demos of some tooling and maybe take some more hands-on practical questions. So I'll start by sharing a terminal screen. Show you the right one. Where is it? Is this it? Oh yeah, this is it. Okay, is that working? Am I sharing anything? Can anyone hear me?
Yeah. I'm seeing it.
Okay, so the main tool that I use on a day-to-day basis for CLVM is Brun. Brun takes a CLVM program as an input and it executes it. So the simplest program is just a quote. And I'm using the dotted notation here because unlike most Lisps in CLVM, quote does not accept multiple parameters. So just everything that's on the right is quoted. So this could actually be a list.
Could you make the will you be able to like make the screen zoom in a little bit? Because yeah,
Try
that's
that.
very small.
That's that.
Yeah, that's much better. Awesome.
Oh yeah, okay. I can see myself. I can see the meeting window behind this window, so that's helpful. And then of course there are operators like plus, which can take as many operands as you want. So plus with 3 gives you 3. Plus with nothing is 0. And as Bram mentioned, 0 and the nil are the same. So Brun sees a nil come out. It doesn't know how to display it, so it just takes its best guess, and it happens to be wrong here. So there's adding a couple numbers. And there's multiply. Div mod, which returns 2 things, 0 and 3. Probably a better example is 300. Well, actually, that's kind of a worse example because here's another gotcha: is what this is actually returning looks like this. 300 divided by 200 is 1, remainder 100. So it's 1.100. But you got to remember that everything is a blob. So once again, Brun doesn't know how to display 1.100, so it takes its best guess and displays it as a program. I think you can force it to display it as a number with -n. Yeah, that's maybe a little less surprising. And there's the sort of atomic operations, like C for cons. I call these atomic operations. I guess that's not really the right name, but these are the minimal operations that you need for Lisp to be Turing complete. So there's cons, and then there's F for first. So I'll do the first of this cons box. That'll pry out the 300, and then R for rest. So that's instead of car and catter or cutter. What else is there? Oh yeah, there's L, which is essentially a Boolean operator indicating if the thing passed to it is a const box or not. So that's false. But if we make it a const box, then it'll become true, which is 1. Then there is if, which is a ternary operator.
I just had a question about the VM. Like, how does it know that something's a cons versus an atom internally? right? Because it doesn't know what one atom versus another based on type, but how does it know that conses are different?
Essentially, a CLVM object is a union type, so it's either an atom or a cons box, so it's encoded in that union type. There's a standard way to serialize these things. Opd is another tool, which is enter disassemble, and it'll. Sorry, opc is what we want. Opd is the opposite. Opc is for opcompile, and opd is for op disassemble. So we can turn this into a serialized version. And the way serialization works is FF means a cons box follows. The 0, 1 encodes the Q. It's because it's just a single byte with value 0, 1, and then the 64 is the 100. So opd, you can undo that, get your Q100 back out.
So what if you wanted to say like something was 255? Is it not possible to actually say, like basically 255 is just not within integer range?
Right, so you can't encode that in 1 byte. So 82 means 2 bytes follow.
I see. Okay, so it's vaguely like UTF-8 kind of similar idea that UTF-8.
Right, it uses some tricks there where it's the length is encoded in the first few bits. So the trick is you look at the leftmost bit, and you keep looking for a bit until you find a 0, and so the number 1s encodes how many bytes the length is encoded in, and then you read, not including the bits that you've just read. So then you read those additional bytes, turn that into a length, and then read the block. Now you'll notice 255 is encoding as a 2-byte 00FF, and that's because the 1-byte FF is -1. So it's 2's complement integers.
Okay, yeah. Just standard encoding tricks the FUs, yeah.
So you can do this, and it encodes as 81FF.
Cool.
Which is different from 82FF because 8200FF, because that's a 2-byte blob with 00FF in it.
Yeah, it basically effectively it has a 0 for the sign bit, so.
Yeah, now opc will also take, so all these, everything I'm showing you here, the symbolic representation is passed to the assembler. The assembler also allows just hex encoded beef style. So that compiles to, as I hinted at before, that the 84 indicates that there are 4 bytes following. And so if you put this in cons box, feed dead beef, this is actually, well, that's actually 2 cons boxes in a tree. So you got the first FF indicating there's a cons box, then the 82 with feed indicating the first atom, then the FF indicating the next cons box, the 84 indicating 4 bytes, then they're spelled out dead beef, and then the 80 is a null. You can see 80 is a null. Anyway, this is the serialization. The serialization is fairly canonical, and it's used in a lot of places. There's one bad thing about it, and that's it doesn't, you'll see a lot of times people doing things like same thing in both the left and the right. And, oh, I'm sorry, I gotta quote this. So if you have this as a data structure, internally, you might have both the left and the right point to the same thing. But when you, let me just copy and paste this. When you dump it to hex, you're repeating yourself. You got the 82 feed and then 82 feed again. Even though internally those two feeds could point to the same thing. So basically there's an opportunity for compression here that the serialization does not do.
Yeah,
So,
I mean, you could support like the Lisp, like common Lisp, the hash operation kind of thing, where you have like a back reference effectively within your data structure. But
okay, that I don't know too much about. See, here's the thing: is I'm not that much of an expert on Lisp. Mostly, I took the parts of Lisp that I needed to make this CLVM work.
yeah, I mean, there's precedence for that. McCarthy took the parts of lambda calculus that he needed, namely lambda, and discarded the rest. So when he created Lisp, so
Yeah, I don't mind being compared to him. That's fine.
Yeah.
So I'm just looking at the questions here. Someone's asking if you run this, you get an error from the disassembler. Is there an ETA in fixing this? OX222222. Oh, I see. Okay. Yeah, that's pretty ugly. Okay, let's do this one step at a time. So 22 is a double quote. So when you disassemble 83222222, you get a double quote, and the disassembler is too stupid to realize that you can't put double quotes inside a double quote. So this is a bug in the disassembler. I don't have an ETA on fixing this, but I do know that the assembler will accept single quote also. Although I think the shell might eat it here. If I get the shell to not eat it, I just do this. Nope, that didn't work. Escape in the shell. What happens if I do this? That doesn't work very well. Anyway, I'm getting a little off topic. So, I wanted to talk about the trinary operator. So this is just if the thing you need to terminate your loops if you're doing recursive programming. So it either pulls out the first thing or the second thing. Now, one thing that I haven't talked about is that run can take an environment. So all these programs, they can just be executed, and it's not really that interesting. But you can also take a parameter, and one means the parameter that you pass in on the command line. So here we're going to get foo.foo back, and this is actually pointer to the same foo because one means take the parameter that you passed in. You're only allowed one parameter, but that parameter can be conv box. So now we have foo.foo. Well, it's not displaying it with a dot for obvious reasons. I think that sort of shows you how it works. But one gives you the parameter, two gives you the left. So this will pick out foo on the left. So now we're going to get foo.foo. And as you might guess, 3 is going to pick out the right. So now we get foo.bar. So when you see an integer like this, a bare integer and as an operator or an operand to an operator, what that means is drill down into the environment and pull out from the tree the corresponding object. So 5, this is going to fail because we're drilling too far into bar, and that's an atom. Yeah, it's expecting a cons. Chialisp.com describes how this tree corresponds to integers, I'll copy and paste that. Let me find it first. Oh, actually, let me look on GitHub. I'm not quite sure where it is on Chialisp.com, but I know where it is on GitHub. But the tree is a really weird looking thing. Node path, there it is.
So I have a question. So the reason you have to quote the numbers is because if you use a number, like a bare number, it's a
path.
Okay, it's a path to the main argument, to the argument that you pass in.
Correct.
Okay, and okay.
Right. So if I quote this, then now, well, I'll quote this one. That now we get the 5 back out instead of bar. Okay, so I'm just going to copy and paste a comment from GitHub. So 1 is the top of the tree, 2 is the left, 3 is the right, and then the numbers start getting weird, and that's basically just an implementation detail, which this comment explains. It just looks at bits and shifts them out to determine whether it goes left or right, which doesn't give what you'd expect where the nodes are in order. So instead of, you'd expect 4, 6, 5, 7 to read 4, 5, 6, 7.
Yeah.
But it doesn't. And since the compiler can actually do the thing where it pulls things out of the tree, it doesn't really matter that much exactly how it works. I've memorized what 1 and 2 and 3 mean and what 5 means. And after that, I just forget about it. I start looking at diagrams. Okay, so that's cons, that's if. Oh, and then there is another special operator, which I call apply. It's really more sort of an eval. And what it does is it changes the environment, or gives you an opportunity to change the environment. So you pass in a program, it's this guy, more parentheses. So this is just going to run this program plus Q2, Q5, and give you 7. But you can actually pass the argument through. So I'm going to pass in an argument 5. The first one evaluates to 5, and then A resets the argument that's passed to its lower thing to this last one, to this guy here. So if I do this, it's going to pull out the 5. And if I do this, it's going to pull out the 6. And that's a little bit confusing, I understand. But to actually do recursive programming, you need to be able to change this environment, because the environment contains all the parameters that are passed to a subfunction, and then you call that subfunction with A. So I used A because it's a long story, but I'm not even sure I could accurately reproduce.
Well, I guess like maybe A for apply, but
yeah, that's what I think is A for apply. It might actually be closer to E for may actually be closer to eval and Lisp. Like, what does eval do in Lisp versus apply?
Apply basically allows you to you can basically apply. The first argument is the function you want to run, and then the rest of the arguments are the arguments you want to apply to that function, right? So you basically say you can actually pick a function in the environment, right?
Part of it's just that it's kind of like recursive, right? Eval kind of recursively evals the arguments, whereas apply just takes all of its parameters as values and just effectively eval will call apply at the end after evaling all of the things that are in the cons cell that apply that eval is operating on. To some extent, you can.
Yeah, so that reminds me of the difference between sort of standard Lisp and CLVM, and that the only two special operators, well, there's really only one special operator in CLVM, and that's Q. It's the only thing that really stops evaluation. Well, and atoms. Atoms are have to stop evaluation because there's no more hierarchy to traverse. I'm trying to find this -I. Where is it? So if in regular Lisp is a special form, in particular, it only evaluates. So if you did this in regular Lisp, it would only evaluate either the Q500 or the Q600. CLVM, the I operator is not a special operator. This is not a special form. It evaluates the left. It evaluates both the true and the false condition, and then just picks out the correct one to return.
Mm-hmm.
So this is a real gotcha for people who aren't expecting this. But the reason that's done is so that the CLVM implementation doesn't need to have different shapes for the operator. It doesn't need to know that some parameters to certain operators terminate evaluation, and it just treats them all uniformly. And in fact, the compiler has an operator called if, which does the quoting necessary and to turn it into the I operator. So maybe I'll show you what that looks like. Here's what run does. Run actually takes what you pass in, compiles it, and then runs it. So it'll compile it to assembly and then run it. So this does auto quoting. So when you go run 5, you just get 5. When you go run 5, 5 plus 100, you get 105. And the main idea with run is it's to be used with contracts. Now contracts, smart contracts, which puzzles essentially, typically start with mod, and then you have some number of parameters, and then you have some defuns, and then you have the actual code. So let's just do something which adds A and B and C. So we'll compile this, and mod sort of means don't run it, but compile it. And so this is what it compiles to. And now if you run this, pass 3 parameters, it just adds them. So once you've got mod, then you can actually define functions. So let's try a fact function for the standard recursive function. If greater than, now I only support one of these operators, greater than or less than. I can never remember which one it is, so I'll just try this for now. If n
greater than is the one that exists.
Is that the right one?
Mm-hmm.
Okay, good.
No, I mean it's greater than.
I think there's no better than I do. N is less than 2, return 1, otherwise return fact times.
I'm saying that greater than exists, not less than.
Oh, so I got the wrong one.
Yeah.
Stupid fingers. That's things greater. Oh, actually, no, I'll do it this way. First times minus n1 and oh, wait.
The simplest thing is to test for 1. Exactly 1 returns 1.
Yeah, okay, I'll do that. Just now, if you put in a negative number, it never stops.
That's true.
Okay, so that should work. And then call it. Just call it with A. Those other 2 arguments will be ignored. Drop a parentheses somewhere.
Actually, if n equals 1, you should return 1. Else, you forgot the. You have to that. There you go. Oh, that's right. Okay.
This is why I love Lisp.
This is why you use Emacs, not.
I think this line needs an extra.
Yeah.
Okay, so. Oh wow, that's exciting.
Yeah, you probably want to put it.
the-
That's probably inside somewhere.
Well,
I don't think you close the definition, the defund.
Right.
There's a missing parentheses after the defund. So go to the last.
Oh yeah. Sure.
Yeah, there you go.
Okay, that. You can't see it, but when I triple click and bash, it does syntax. It does parenthesis matching. Oh, actually, no. I guess you can see it. You can't see it if you're using Tmux. That's how I usually share the screen. Okay, so it actually printed something out. So this will, with a little luck, actually work.
So it just factorials the input.
And then it takes 2 extra parameters, which are not going to be used anyway. Okay, that looks right. It's in hex, so it's probably not that recognizable to most people.
Hooray.
Okay, that looks right. So you can see it starts out with an apply of this nonsense. This is sort of the Y Combinator, where it takes factorial, passes it into itself, and then passes in the other arguments. And this is the thing that modifies these arguments, passing in the compiled version of the factorial function.
So what does a queue with 2 arguments mean? Like there's a left-hand side as well on some of them.
Right. So it is a little confusing, but if you think that this is the same as this,
okay,
that becomes obvious.
I see.
So it's, again, this is just the disassembler doesn't know the best way to print it.
Yeah, that's why in Lisp the quote operator is not defined the way like that way in terms of taking the second part of the console and having that be the quoted thing. It's the second, right? It's the whole expression there. This the second element of the list.
Yeah, I think it does a rest first, right?
Right. Well,
So,
yeah.
Yeah,
It
2
takes
arguments
the
is
car of
two
the
consoles instead of 1.
Yeah.
sorry, say again?
It takes the car. It takes the car of the cadre as the parameter to the quote, rather
Right.
than just the cadre. So
And
that
since-
syntax looks nicer.
And since quote is used so frequently in programs, we decided that by just doing cutter instead of car cutter.
Yeah, you might save a little bit. Yeah.
Right,
Yeah.
especially when
That's,
coding.
because that's your compiled format. In Lisp, that the compiled format is not.
Right.
No,
So,
Lisp is not the compilation target for Lisp.
right. So what goes on the blockchain is this nasty hex string.
Yeah.
So we save an FF for every quote and a 0 for every quote by doing it the way that we're doing it.
Right.
Can you show us a little bit on, of how an if expression compiles to an I expression?
Yeah, probably this example here is the best. So here's the if expression, and here's the corresponding I expression. I'll just paste them down here so that you can look at them in a vacuum.
So if I understand right, it just quotes the outputs, right?
Yes, that's right. So the 5 corresponds to the n, and that's because n, you got to look up in the tree. N is the first thing. Well, I guess it's actually it's f of r, I think, which corresponds to 5. And then this q1 is this one. This 18 corresponds to multiply. And then this apply corresponds to the recursive fact. So 2 is where we've hidden the implementation of the compiled implementation of fact. And then so we also have to pass that compiled implementation of fact and then update the parameters.
So you said that -n will force it to return a number. Is there like a similar way to make it return a string or a hex string or something like that?
Yeah, there is. Go back to the Bram. Go -x oh, sorry. That -d lets you put in hex input, and -d will let you output hex input, and then so you can feed this to opd. Okay. And so the nice thing about this is you know exactly what you're getting. Because
Well,
the serialization
like
is canonical.
what if the result of the program is 5, but you want it to print as a hex string, like 0x05 kind of thing?
Yeah, that should work too.
I thought -D assembles it for you.
What -D does, well, let's see what the help says about it. It forces the output to be, okay, dump hex version of final output. I wrote that. It says it better than I can say it now.
Okay.
So that's just applied at the end. It's just how the result is printed. Right, because you run your program, you get a CLVM object as its output.
So -N just makes it output as a value, not a program. That makes more sense.
What it does is it tells the disassembler to not ever interpret it as a program. So you can see it here, no keywords.
Okay. Yeah.
So Q-1.1.
I figured the N stood for
a bunch of ones, so it says Q.1.
Mm-hmm.
Might be a little easier to see if we do this. So you can see it's a 1 and then a pair of ones. Then if we go -N, we see it doesn't turn this one into a Q.
Yeah, that's pretty useful because I've printed out the result of my programs before and then gotten a bunch of random operators instead of the actual number.
Right, and I definitely agree. It's extremely disorienting the first time that happens to you. You're like, why are these operators appearing? And you got to go back. It all comes down to the fact that there's only one type of atom, and so the disassembler can only just guess on how you want it to look. All right, but then you can do some sort of nasty assembly language style things where you have a value which is used as both a constant and as an operator, and that's the kind of thing that people who write copy protection love to do.
So
not sure if you really want to copy protect your coins, but
there's one question I have been wondering for a while. It's what the actual exact difference is between defun inline, and def macro.
Oh, okay. So let me come up with some examples. We'll take two parameters, A and B, defun, F1, just add A and B. Wrong. Oh, no parameters.
My understanding was that defun uses apply, but defun inline doesn't, or something like that.
Defun inline, it turns your function declaration into a macro. Forces it inline. So you can see the second program is way smaller.
But then what's the difference between that and def macro?
It's really just a syntax thing. So you could write this yourself as a macro. Def macro F1 takes A, B. You probably want to use quasi-quote for this.
Oh, so the inputs of the macro aren't evaluated by default, basically?
Right.
Okay.
I think this is actually what defun inline does. Okay, I forgot something. Where is it? So if I did this right, you'll get the same output. Okay, yeah.
All right, cool.
So you can see if you really just want an inline function, defun inline makes it look a lot nicer than def macro.
Yeah, def macro will let you mess with the actual syntax that was passed in.
But so you could implement your own if statement or something like that with def macro, for example.
Yes, in fact, the compiler does implement a lot of its operators as macros.
I see.
Yeah, that's a classic way to implement things in Lisp. There's a whole series of meta-circular operators in Common Lisp, where one can be implemented as a macro of the other, like pairs. And so, but one of them has to be implemented at the sort of bare metal level, right, to actually resolve to something. But they can both mutually be implemented as macros of each other in theory. So yeah, you're given basically the raw syntax tree that's inside those parentheses, and then you get to manipulate it into whatever other operation, other control structure you want it to actually execute.
Yep.
In fact, Henry Baker has an article that presents all those.
Yeah. Probably if you Google for H. Baker metacircular, you'll.
It actually might be a good crowd to look at some of the compiler tools. So the way I did the compiler is there are 3 stages. The stage 0 is nothing; it's just the assembler essentially. Stage 1 was a dead-end experiment that I did for Bram that we ended up not using, and then stage 2 is a compiler behind the run.
Yeah, I had to dig through this when I was trying to compile from Python directly.
Oh, okay. Yeah, it's kind of a mess, but it sort of works. The operators are built up so sort of in a hierarchy like this. These are the default built-in operators, and the first one is def macro, as you can see. But you get stuck in this loop where you can't define def macro in terms of def macro, so you have to define it in assembly language. So this is what we want to compile, but we can't start there. So I just want to compile this in my head and then turn it into this, or maybe I compile it with an earlier version. But this will compile. This Lisp will compile to this assembly. Yeah. That's kind of nice. And then I had to implement list.
Oh yeah, what does that hashtag in front mean? I've been wondering that.
Oh, that it's optional, but it emphasizes the fact that I would like to assemble this operator as its numerical value and not as a string or a symbol or anything.
Okay.
So it's more sort of a comment to the reader. Probably should have made it a requirement.
And is there any way to do compile time evaluation? Like if you want to have a macro that loops through each of its parameters and changes them in some way before.
Well, yeah. Yep, that's very standard def macro stuff. So you can see this is the implementation of if.
And so can you use them recursively then?
Yes, the macro can be recursive. There are some examples somewhere. Where are they?
This is going to be really useful for writing a compiler to CLVM.
Let me open a new tab here and find what this is. Just give me a sec here. I'm working in another window.
All right. Because I've been trying lately to implement like a sort of scripting language that compiles to CLVM.
Yeah, I mean, you can definitely do that.
Yeah.
Okay, so here's a CLVM runtime directory. This is in GitHub too, in CLVM tools. We define some Chia constants here. These are for creating output conditions. So that's the exhaustive list of conditions as they exist right now.
I thought there were more than that.
You're right. This must be old, and the numbers are wrong. I think we renumbered them. I must have not updated this for a while. Let me just do a git pull. Wrong.
It should be like cdv clsp retrieve condition codes.clib, I think.
Okay, well, this is where I have main. This would be a little better. That's also not up to date. But these macros, so here's an example of a lazy evaluation of AND.
Yeah.
Just basically does a lot of embedded ifs and calls itself recursively.
So it's the same as all, but it's like short circuiting basically.
Yes. So all will evaluate everything. Because it'll go down the tree entirely, and if the second parameter, for example, raises an exception and ends the script, and that'll do something different than this AND will, because the AND won't bother dealing with things after its first failure.
So as far as cost, would the macro be more efficient?
There is no hard and fast answer to that. It depends on what your expected it depends on how expensive it is to evaluate the operands and how often you expect them to be true and false. So it's a branch prediction problem.
Okay. And speaking of cost, I never saw anywhere where it mentioned like how much cost you actually have or get, or like what you have to pay to have more or anything like that.
Oh yeah. Okay. So because this is a Turing complete language, we've got the halting problem, which means we never know if our program is ever going to halt, and we don't want a coin spend to lock everything up. So we just do what Ethereum does, and every operator has a cost, and a block has a maximum cost. And if you exceed that maximum cost, then the block fails, which means that we know how much CPU we can throw at a particular spend before giving up.
Now, if a spend fails because of cost, will it be retried in the next block, or will it just go away?
No, because it will, unless you change the solution, it's going to run deterministically every time. Okay. And so the cost will always be the same.
Well, so if it happens to be thrown into a block that's almost full, could it potentially fail even when it should succeed?
Well, it would cause the entire block to fail, which means the block wouldn't be good and everyone would just ignore it.
Okay. Make
sense?
Mm-hmm.
This is another interesting thing. It's the only hash function we support is SHA-256. So we came up with this notion of a SHA tree.
Definitely use this a lot.
Yeah, we use this everywhere. This is how a puzzle hash is defined. It's just a recursive implementation of SHA, but giving every node a SHA value, and you can do it recursively, which means that if you know the SHA tree value of the subtree, you can just substitute that in rather than evaluating the SHA value, rather than going down the entire tree again. And that's really useful for doing shortcuts. Like if you have a puzzle type and you want to be assured that the child puzzle is of the same form.
Yeah. The really confusing thing like this was the puzzle on tree hash one, where like it queries in to a puzzle hash. The implementation of that was really hard to understand.
Yes, I think you're talking about this.
Yeah.
This is actually not very good code. We have a newer version of this, which is better.
Yeah, I'm using the one that's in Matt Hoff's Chia Dev Tools.
Yes, that one will be up to date.
Yeah.
I
believe it's called curry and puzzle hash or something like that.
Right. So I don't know how much currying or partial function application is used in Lisp. It seems more like a Haskell thing to me. I'm not a Haskell expert either. But essentially the idea of currying is that you have a puzzle that takes several parameters.
Oh yeah, the currying part makes sense. It's just more the implementation that was confusing for that.
Oh, right. No, I mean, I know you understand. I just don't know how widely understood this is in general.
Yeah.
You're probably more likely to find people talking about partial evaluation than partial application in Lisp circles, but yeah.
Yeah.
Yeah. So our trick is that when you create a puzzle template, one of the parameters might be something like public key. And so you want that public key to be defined at the time the coin is created, so that it's locked in, so that basically you can use that public key as the public key for the coin. So it can only be spent by someone who has the corresponding private key.
Yep.
Which means that your mod, you actually want this public key parameter to be a constant. And so that's what currying gets you there.
And you do that with apply with the environment is just a cons of whatever you're currying in, and the environment of the outer function or whatever.
Right.
So if you have a puzzle, you would wrap it in an apply with a cons box of the curried in value and the environment.
Yes, exactly.
Yeah. Yeah, I mean that's how you normally do it in Lisp. Like that's why there's not much discussion about it, because it's just like, yeah, you just capture the argument in a closure and call it later with the other arguments. That's all it is.
Mm-hmm.
Right. And so the way closures are implemented is using this A operator. When here's the capture essentially.
Oh yes. Yeah, I was curious how soft fork will work in the future, or like how would you use that in like practice?
Right. So soft fork is a weird operator. Let's take a look at the implementation.
Yeah.
I'm going to go back.
Because the changing the way that Chialisp works seemed like something that would be done outside of Chialisp itself, but apparently not.
Right. We essentially need a new dialect of Chialisp. So let's look at the, even though this is not the canonical one, this is the reference implementation. So let's look at Python, even though there's a Rust version, which is a zillion times faster. And so the soft fork operator, it's basically something like this. Soft fork takes at least one parameter, and it returns 0, no matter what you pass in. But one interesting thing about soft fork is that the cost of it depends on the first argument.
And the queue is just getting added on to that or something?
Yeah, there's an extra 30. Basically, the wrapper. Well, the queue is going to cost something, and soft fork is going to cost something.
Okay.
A minimum value, and there's also just like this wrapper calling into Brun, which is written in CLVM, so that sort of throws on some extra cost, I guess.
So if you're writing a program with soft fork, why would you want to set the cost of anything? Couldn't you just set it to 0 and have whatever inside of it?
Right. Well, so the idea is soft fork is going to introduce new operators. So let's say what happens is soft fork takes this value as the cost, and then it runs this program in a whole new version of CLVM that maybe has new operators like cosine. 5 times pi. This is quite ridiculous, obviously, since cosine wouldn't be very useful unless you had floating point, or at least something like that. And then soft fork ignores it. But probably what you'd want to do is you'd want to check to see if a parameter you passed in was equal to cosine 5 pi. So maybe like 2. And right now, it just completely ignores that. But a future incarnation of Chialisp might take soft fork. I think soft fork also takes a version number. Or I mean, I think that's what we're expecting. So this is like, okay, this is like version 2 of CLVM.
So it's not
cosine in it.
So soft fork doesn't actually do anything yet, essentially.
Right. It's a placeholder for later, where a version 2 version of CLVM, when it sees a soft fork and it sees this Q2, now it knows, okay, I got to start paying attention to cosine.
Okay.
So there's two things that this program can do. It can either return nil, like it does now, or it can fail.
So then if you have a future version of Chialisp, would it would compile with soft fork in there by default or something like that?
I guess you'd write the compiler to, if you had a cosine, make sure that you're within the soft fork context that has cosine in it.
I see.
And so what you do is you'd pass in a value, which should be argument number 2, and you'd compare it to your calculated value of cosine 5 pi. And I guess what you'd want to do is like assert equal. And then you could fail if it were false. And so the old clients would accept it because they don't know about this soft fork. But the newer clients that do know about the soft fork would reject it. And as long as they're 50%, now this cosine actually, this assert equals and this cosine actually have some effect.
I see. So this is kind of an off-topic question, but all of the characters like equals, plus, and then alphanumeric characters, they can be combined at will to create identifiers.
Yeah, that's a high level. That's a Chialisp question, really, and I think that's what Chialisp does.
Because you have assert equals there as one identifier, and
that's supposed to be a new operator.
Yeah. Oh, okay. And like greater than s is one that has both as well.
Oh, sure. Yeah, I mean, parsing Lisp is pretty easy, right? Because you just look for parentheses and white space and spaces.
Yeah.
And especially when you don't have symbols, like this language doesn't.
Also, is the future versions of Chialisp going to allow string escapes? Because currently / is just treated as a normal character.
Right. You don't technically need them because anything weird you can just do like this.
Yeah, hex. Mm-hmm.
That's not gonna work.
Yeah, I guess there's downsides to escapes as well.
Yeah, and I mean, you got to remember the domain of this language. The inputs are going to be CLVM objects, and the outputs are going to be conditions. You're not going to be doing a lot of string manipulation, except for in toys.
Mm-hmm.
Yeah, this is another important operator which I haven't yet mentioned. X, which takes an arbitrary string and returns it and fails.
It's like raise in Python, right?
Yeah. Okay, that failed for the wrong reason. That failed because foo was a bare atom. Okay, there. Mm-hmm. So it failed because CLVM raised foo. So this is good. This is fine for debugging, but normally you just want to, in a real contract, you just want to do that because it takes less code.
And the error is never actually used anywhere.
Right. The error can be displayed to the end user, which, unless the end user is the debugger of the contract, is not going to care.
Yeah.
I have a question. So what you were showing us originally was like the basic level language, right? Like I see there's a lot of library functions like cosine and things like that.
Well, that's pretend.
I'm sorry.
The cosine was pretend just for the.
Oh, okay. I missed that. Yeah, because I was going to ask about some of these higher level things, like, okay, how did it know that? But like I'm like, wow, this language has a lot, like defun or whatever.
Yeah, here's let me find the exhaustive list of operators.
It's on chialisp.com/doc/ref/CLVM.
So the dot is just a placeholder, which means 0 is not used. Then there's quote, apply, if, cons, first, rest. Can you see the cursor? You can. Okay.
Yeah.
Yep.
List and raise. And then these operators are for strings. There's equals, greater than s. So that does a string comparison, like strcomp, similar to strcomp, not exactly. SHA-256. It's really the only hashing operator. Substir, strlen, concat, these all do what you would expect. Plus, minus, times, divide, div mod, greater than, ASH, LSH. I stole these names from Emacs. I'm not sure how widely used those names are, but I just wanted to steal them from somewhere so that I wouldn't have to document them. Same with the logical operators, log and, log I, or log X, or log not. One thing it took me a while to realize is that I should treat these not as strings, but as ints for these log operators. And then a couple BLS 1381 operators.
Yeah, those are confusing to me. I don't understand what they do.
Yeah, you have to have a good understanding of ECC, elliptical curve cryptography, to know exactly what they're doing. But essentially, it's discrete logarithms. So this is discrete. This one here is discrete exponentiation. So it takes an integer, and then it gives you this weird object, which is an elliptic curve point, and then this lets you add 2 elliptic curve points. So you can take 2 public keys and add them together to get a new public key. And essentially, you need each private key to you need the sum of the 2 private keys to be able to sign the new public key. And then some Boolean operators. These names are stolen from Python. And then this weird soft fork operator that I discussed just now. And that's it.
So what does the dot operator do? I've never actually used that.
I think it's just a Boolean not. So yeah, you either get 1 or 0 out of it.
Oh, so dot is the same as not?
Not is the same as, would you say not is the same as not?
Oh, I was asking what the dot operator did, not.
Oh, the dot operator. That's a placeholder. That's not an operator.
Oh, okay.
It just means this operator isn't real. I think there's actually some code that explicitly ignores it.
So if you use it, it'll just
see right here, if it's QA or dot, it doesn't go into the dot. It doesn't go into the table.
Okay.
It's just because I didn't want to use 0, and I wanted to leave some space in case we want to add a new operator here later. Because and also I think I wanted the operators to start on nice looking boundaries.
So I have a question. In your factorial example, when you defund the factorial, you mentioned that the final hash is what's ultimately going to go into the blockchain, and you said that the references of the factorial you would normally in the disassembly code, or it may have been in the opc code, there's like 2 that references the actual function pointer to the factorial that's ultimately been defined. Is the entire program including that and plus whatever additional library functions that you may be using from, like, say, soft fork or whatever, is that going to ultimately be encapsulated into that single transaction that gets added into the blockchain? Or like if you're using contract kind of functions that you've defined, is that all encapsulated in that hex string that you showed, or is there?
Yeah. Any functions that you use are going to have to be included. Not actually at the coin creation time, but at spend time. Like the coin actually looks like this. It's a parent hash, so that's 32 bytes, and then puzzle hash, which is another 32 bytes, and then an amount, which is a varant. It's essentially a CLVM integer indicating how much that coin is worth. Now, the parent hash is just the name. It's just the hash of the parent coin's entities. So you hash this and you get this coin ID. Wider. There we go. Now it fits on one line. So the puzzle hash uses that SHA-tree hash that I was alluding to before. Now, when you spend the coin, you actually have to reveal the puzzle. So people can't see your puzzle until you actually spend the coin. So you reveal the puzzle. It has to match the puzzle hash. If you spend, you include the puzzle solution and something else. I can't remember what it is, but the key is that this puzzle must match the hash. And so this is why you want to keep your puzzle size small, because spending the coin, you incur the cost of storing those bytes on the blockchain.
Someone mentioned it looks like the amount is also going to be in there. The amount is the puzzle solution and amount. Is that supposed to be in there? Okay.
Well, that's in that's so these 3 things here. No close quote. These 3 things here. That's the definition of a coin. It's these 3 fields, and that's stored in the coin database.
Okay.
So when a new coin is created, that goes in the database, and then when it's spent, this comes out of the database along with the fact that some metadata about when the coin was created and whether or not it's already been spent.
So you mentioned that that the puzzle hash is a secret and it has to be revealed. Who reveals it?
When you spend it, it gets revealed.
The spender, yeah.
Okay.
I have a wallet which contains information about all these coins that.
Oh, I see. You got okay. I see the spender. Okay, that makes sense.
Right.
Okay. So the puzzle.
Since it's coin, I presumably know what the puzzle is corresponding.
Yeah,
to.
exactly. I see what you're saying. Now I get it. Okay. Yeah, I got a little confused there for a minute, but now I know. Yeah.
The owner of the coin is who knows how to solve the problem.
Yeah. So the person who created this coin in the first place from some other transaction in the past,
I mean,
they create a puzzle, and then if they want it, then anyone who can solve the puzzle can actually dictate where the amount goes. Okay.
Right. And create some
only
coins.
the spender would know. It would be the spender's secret. It's the spender's job to keep the puzzle secret.
So, like, if I want to send you money, you're going to create a puzzle and then send me the puzzle hash as an address. The address is the same as puzzle hash, just a human readable version. And then I send coins to that puzzle hash, which now are basically yours because you know what the puzzle is and you know how to solve the puzzle. The puzzle probably has a public key that only you know the private key to.
Mm-hmm. Okay.
And also typically the puzzle includes a way for you to set the output conditions for when you spend the coin. And those output conditions let you determine how that coin creates other coins, or maybe joins with other coins that are in your wallet to, create a larger coin.
Okay, that actually makes a lot more sense because I think so. Probably some of the terminology is different from here than in Bitcoin. So, and puzzle is a new type of idea. At least I've never encountered it anywhere else.
Well, it's a what is it? SIG hat, script SIG or something.
Okay.
I forget the real name.
Okay.
Script hash? Is that basically what it is?
Yeah. Is it? I forget the Bitcoin names. I have a Bitcoin project called PiCoin, and I didn't use those names. I think that's where I came up with the puzzle moniker. And so that's just how I always think of it.
Yeah. Actually, I like the name puzzle. It's a good.
It's more complimentary with solution and an intuitive.
It's 9/10 of software figuring out good names. So you did a good job with that because I don't think anyone's ever actually used the puzzle before as a name.
Well, I have to say that if the original Bitcoiner had used puzzle and solution before, he would never have attained the air of mystery around him that made Bitcoin such a success. So it was good PR to use obscure and mysterious names. But I'm glad you're not.
Well, everything I needed to know, I learned in kindergarten. That's what I like to say. That's where I learned SHA-256.
Wait, what?
Man, that must have been some advanced kindergarten.
Yeah, my teacher was rough.
Not really that hard. It's about, writing a note on a piece of paper and scrunching it up and then reading the note without unscrunching the paper.
Right. How come you kids don't know secure hashes yet?
I know. They got to start upping the ante in kindergartens. That's what I've been trying to advocate. We want them to go directly into crypto and functional programming from kindergarten. Actually, I have a couple of questions on YouTube. I like to bring them up. Actually, one was before, but maybe you can answer this. How are things progressing with the hackathon event?
It's about to end tomorrow.
I don't have much insight into that, so I can't really comment.
Okay. Also, that was from Ziklan Nagoric. Sorry, Denny's Rashid. Gerald Neal asks, the way SHA-256 tree works seems like a process very specific to Lisp and cryptocurrency. May be interesting to discuss. You interpret what that means.
It's not specific to cryptocurrency, but it's specific to Lisp.
Yeah, it's very specific to Chia. So SHA-256 tree you could define it recursively. For an atom, it's essentially the SHA-256 of 1 plus the atom as a string. And then, for a Conn cell C1, C2, it's essentially SHA-256 2 plus SHA-256 tree of C1 plus SHA-256 tree C2. So essentially you have a SHA-256 operator for each atom. But if you ever know the tree hash at a certain node, you can stop evaluating there and just substitute it in. That's the trick.
Mm-hmm. Yeah. Well, there's that.
So if SHA is secure, this should be secure too.
And this is basically like a regular Merkle tree, what they call it in the literature, right?
I think it's
Or is it different?
It's not quite a Merkle tree. I guess it's an extension of a Merkle tree because a Merkle tree, I guess a Merkle tree does have two types. It's because a tree is either a leaf node or a Merkle tree. In a Merkle tree, it's either a leaf node.
Keys are, I think okay, so it is a little bit different. Okay.
A little bit, but same idea.
Yeah, yeah.
Where you don't have to reveal everything. Yeah, and actually that's a thing. That Merkle tree, that's a good example because like a SHA, you could have a tree of possible puzzles. So you could have a puzzle say, you can use any of the puzzles in this tree and give the tree hash for that. And then you give a Merkle style reveal of it to the puzzle that you actually are concerned with when you spin. And so that's a way of implementing, like a puzzle that you could spin using 1,000 other puzzles, any of 1,000 other puzzles. So like it's a way of doing M of N, for example. Although it's a bit complicated generating the Merkle tree, but it's just code. So I've gone all over the place. I'm not sure what a natural thing for me to show next is, or if there are any questions or requests. I've scrolled back in the chat for a bit.
So will the soft fork be something the Chia team implements, or will it be something that community can?
That's more of a political question, and there seems to be this trend that the more you know about technology, the less you know about politics. So I'm just going to say I don't know.
Works for me.
Does anyone want to see anything else?
I think that's it for me.
Okay.
Not much more to know.
Yeah, we've had a long stream anyways, about 2 hours and 20 minutes, which is amazing. So wait, first an announcement to everyone on the conference. After the live stream ends, we're going to continue, if you want to continue hanging out and socializing, get to talk to your fellow LispNYCs, just stick around. Let's see. Could you stop sharing your screen so I can put my video up? Yeah.
By the way, thank you, Richard.
There we go. Okay. So and so I want to thank I want to thank you, Richard. I thought the demo was excellent, and the questions were great too. I've been riveted for the last hour. I also want to thank Bram for his amazing insights. I want to have a special thank you to Oliver, who suggested this talk, who is a member of our community, and which also reminds me that if any other members, including those on YouTube, if you have a talk that you have an idea for, you can send the request to speak@listnyc.org by email, or you can hit our DMs. We're at LispNYC. You can find me around. You can check out our website, lisp.nyc. That's the URL. And yeah, and I want to thank the YouTube guys. And I just want to remind you, if you're on YouTube, remember to like the video, because remember to like the video. Remember to subscribe so you can see other fantastic Lisp talks. Check out our other videos on the channel. Hit that notify bell so you'll be immediately when new videos get posted up, you'll be immediately notified. And with that, I think I'll just close the parentheses. So see you next time.